Good morning, everyone. Today we are covering a new topic, ionizing radiation. We'll be talking about nuclear processes that results into the radiation of alpha, beta, and gamma. Lots of the radioactivity we get exposed to in our life are natural, and they are not necessarily seriously harmful. All decay processes transform less stable nuclei into more stable ones. How does this happen? We will start first with the alpha decay. In alpha decay, we release a helium nucleus such that this helium nucleus has a mass number of 4 and atomic number of 2. What do those numbers mean? We will look into that more in detail. So if this is my parent nucleus that has a mass number of 226, I'm calling it A, and an atomic number Z of 88. The Z represents the protons number, and the A represents the summation of the protons and the neutrons. So in this case, I have this radium nucleus that's going to decay and give a daughter nucleus of randon. This randon, as you can see, has less uh, mass number by 4 and has less atomic number by 2. That's why this nucleus has now transformed into another nucleus, and this resulted in the emission of a helium nucleus, and this is what we call the alpha decay. So, as I said before, it will happen such that the mass number before the decay, which 2 to 6 in this case, equals to the total mass after the decay, which is 2 to 2 plus 4. And the total charge before decay also, which is the Z number here, 88 equals to 86 plus 2. So they have to be balanced. Those two numbers, they have to be balanced between before the decay and after the decay. And this is what we call the alpha decay. So there will be energy, as a matter of fact, released due to this decay. How do we calculate this energy? Here, the nucleus unified mass is given to me for the radium, and this is the unified atomic mass given to me for the random, and then this is the helium. In this case, I will calculate the mass before and the mass after. So if you look at this one as the mass before and the summation of those two as the mass after in unified mass unit, then the difference between those two numbers represents the amount of mass that will be converted into energy. So this is the total before the decay coming from here, and this is the total after the decay coming from the summation of those two numbers. Then the difference of the mass is 0.005222 unified mass unit. So the mass has been decreased by this number. This is a mass unit, unified mass unit. If you multiply it by this number, every one unified mass unit equals to 1.66054, 10 to the power minus 27 kilogram, you will get the total mass in kilograms. Now, how much is this energy? We can get the energy from this expression, that is delta E equals to delta M times C squared. So what is delta E? What is delta M here? Delta M is the mass we found in kilograms after we multiplied this number with this number to get the mass, the delta mass in kilograms. It will be now this number. Then multiply this number by the c squared, which is 10, 3 times to the power 8 squared, and then you will get the delta E in joules. This is the released energy due to this decay, due to this alpha decay. Now, if you divide this joule number, which is 7.8 to the power minus 13, by how much is the electron volt, then you can get the energy released in electron volt. So this is 1 electron volt equals to 1.602 10 to the power minus 19 joules. Divide your energy number by this number, then you can get how many electron volts. As simple as this. So let's look at this example here. In this example, we have, this is the parent nucleus, uranium, with a mass number of 298 and an atomic number of 92. In alpha decay, it will release a helium nucleus plus a new nucleus. What are the A and B in the decay equation above? So definitely here, the helium has A equals to 2. So I have A equals to 2 for the helium. The atomic number for the helium nucleus is 2. Then what am I missing? I'm missing here, this B has an A and Z, where A is the mass number and Z is the atomic number. So in this case, if I take 92 and subtract 2 from it, then Z would be 90. And then 298 minus 4, this one would be 294. So now B, which nucleus is that? Is it, I have 294 and 90 with 2 here. And I have 294 and 90 with 2A here. However, here I have thorium and here I have calcium. Then definitely the thorium is the nucleus that will be the daughter nucleus from the decay that's happening in uranium. So answer is 2. Okay, so we have an example here where we need to calculate the energy released in the alpha decay of that thorium 230-90. Okay, so we have the mass before as 230.033134, and then the mass after, total mass after, as 226.02541 plus 4.002603, then delta M is 5.131 10 to the power minus 3. Then if I want to calculate delta M in kilograms, then I take 5.131 10 to the power minus 3, 1.66054 10 to the power minus 27, then delta M equals to 8.52 10 to the power minus 30 kilograms. Then delta E equals to delta M in kilograms times C squared, or delta E equals to 8.52 10 to the power minus 30 times 3 10 to the power 8 squared. Delta E equals to 7.67 10 to the power minus 13 joules. Now if I divide this number, 7.67 10 to the power minus 13, if I divide this number with the equivalent of the electron volt, which is 1.602 10 to the power minus 19, I get delta E equals to 4.79 mega electron volt. Now let's move to the second type of decay. We have a beta decay. To be specific here, we're starting with the beta minus decay. In beta minus decay, we have the nuclei transform through the emission of a beta particle, which is the same as the electron, which means in this case we have one neutron in the nucleus is replaced by a proton and an electron, which is the beta particle. The proton remains in the nucleus. The beta minus particle is ejected. So this is going to result into an increase into the Z number. However, A will stay the same. So it's different than the alpha decay. In alpha decay, we have the A number and the Z number changing. In beta decay, due to the neutron being replaced with a proton, then the Z number will increase. However, the A number will stay the same. And we have the beta minus particle emission out of this nucleus. So let's look at an example here. So in this example, we have a C14-6, which means the atomic number is 6 and the mass number is 14. Due to the beta minus decay, my neutron here was replaced. So if I am here to look at the neutron, as we have 8 neutron and we have 6 protons. So what's going to happen here is one of the neutrons, so this is for the C, one of the neutron will be replaced by proton. So here for N, I have N becoming 7, and I have P increasing becoming 7. So what's going to happen? What does this mean? This means that the total A is still 14. A did not change. However, the Z number has increased. So beta minus is going to result into an increase in Z. So Z now went from 6 to 7. And then I have the beta particle emission, which is in this case an electron plus an anti-neutrino, which is here. V, this is an anti-neutrino. So the beta minus decay is going to result into an electron emission plus an anti-neutrino plus a transformation in the nucleus such that the A number stays the same. However, the Z number will increase. So beta minus increase in Z number plus the emission of one electron and one anti-neutrino. For the beta positive decay, the radioactive nuclei is going to transform into a new nucleus, going to go from one nucleus to another, and this is going to result into a decrease in the atomic number and an emission of a positron, which is the same particle of the electron. However, the charge is the opposite, and also a neutrino. So we have the Z number will decrease here. One proton is going to be replaced with a neutron, so the mass number will not change. So what's happening here in the nucleus is the opposite of what happened in the beta minus. So let's look at this example. Here we have F with F. We have N equals to 18 minus 9, which is 9. We have the protons equals to 9. However, for O, the one proton is going to be replaced with a neutron, so N becomes 10, and now the protons becomes 8. And as you can see, if you add those two numbers to get the mass number, then 18 is going to be the mass number, it will not change. However, the proton number has decreased by 1. And also will accompany this a positron, which is the same mass, however, opposite charge than the electron, and the neutrino. So we have the neutrino and the beta positive decay, and we have the anti-neutrino and the beta negative decay. And we said that the difference between the neutrino and the anti-neutrino that they spin in the opposite direction. However, they have zero mass and zero charge. The emission of gamma rays is different than what we have seen so far. Gamma rays are high energy electromagnetic radiation, which basically means high frequency and short wavelength light. So in the gamma radiation, there is no electric charge, no charges, and no mass. Just the release of the energy from the nucleus. No change in the nuclear configuration, so the mass number and the atomic number will not change. As you can see, A and Z here are the same, only a release of energy in terms of the gamma rays. We have seen 4 kinds of decays so far. We have seen the alpha decays, which is basically results into an emission of helium nucleus, and this is going to result into a mass number decrease by 4, and an atomic number decrease by 2. The beta minus decay is going to result into an increase in the Z number. However, A number is going to stay the same with an electron and an antineutrino. The beta positive decay is going to result into a decrease in the Z with positron and neutrino particles, and gamma decay is going to result into an energy release in terms of gamma rays that are electromagnetic radiation in nature, a high energy of electromagnetic radiation, and has no charge and has no mass as well. Now let's look at this example. In this example, we have the following. We have Ca3820 that has decayed into K3819. So the mass number did not change. A is the same. However, Z has decreased. If Z has decreased, if you recall, this basically gives me an indication that this should be a beta positive decay. Why? Because in beta positive decay, we have the Z number decreased. Here in the second one, I have the atomic number decreased by 2, mass number decreased by 4, and this basically means this is an alpha decay because I have the mass number and the atomic number changing due to the emission of the nucleus, of the helium nucleus. Then the last one is K4019 is giving me Ca4020, so A number did not change. However, the Z number now has increased, which is opposite to what happened here. So definitely this is a beta minus. So the beta positive is basically Z is decreased, then beta negative is Z has increased. So the answer is A. So what's the difference between the beta positive and the beta negative decay? One of them is happening due to the decrease in the Z. The other one is happening when I have an increase in the Z. So this means that if I have some nucleus that are unstable due to the difference in the numbers, then this is the way to create a stability. So in this case, if the Z is low in the nucleus with respect to the neutron, then in this case, the way to decrease the number of neutrons and make the protons higher is to have a beta negative radiation to make them equal or close to equal. In case the Z number is high with respect to the neutrons, then in this case, I need to reduce the number of Z. And in this case, I have a beta positive. It's going to reduce the number of Z and make them equal or close to equal in this case to reach the stability. So one of them will result into increasing the number of protons. The other one will result into decreasing the number of protons. It depends on the ratio between the Z number and the mass number, the radiations happening that will achieve stability is either beta minus or beta plus. So if we said that the beta minus is going to result into increasing the Z number, if the Z number is way less than the neutron, and the beta positive is going to decrease the Z number if the Z number is higher than the neutrons in the nucleus. Okay, so this is the table, and as you can see, those blue squares represents stable material where N are either equal to Z or close to Z. So this is those blue squares represents the stable material. Okay, examples here we have Ne 1810 is unstable. What type of beta decay does it undergo? Write the decay equation for this process. So we know here that N equals to 18 minus 10 equals to 8, and the protons are the Z number here 10. So we need to go with a decay that would decrease the Z number, which basically means beta positive decay, because beta positive is going to result in decreasing the Z number. So here I have 18 Ne10 is going to result into F, also 18. However, now the number went down to 9 plus the positron plus the neutrino. Mg2819 is unstable. What type of beta decay does it undergo? Here I have N equals to 28 minus 12 equals to 16. I have protons as 12. In this case, I need a beta decay that will result into an increase in the Z number, which means beta minus. So the equation for this is going to be, we have Mg 28 12 resulting into Al 28. The number here will be 13 plus the electron plus the anti-neutrino.